To convert ohms per foot to milliohms, you multiply the ohms per foot value by 1000. For example, if the ohms per foot is 0.5, the milliohms would be 0.5 ohms per foot multiplied by 1000, which equals 50 milliohms. Therefore, to find the impedance in milliohms for a particular length of cable, you would multiply the ohms per foot by 1000, and then multiply by the length of the cable in feet. For instance, if the ohms per foot is 0.5 and the cable length is 100 feet, the impedance in milliohms would be 0.5 ohms per foot multiplied by 1000 multiplied by 100 feet, which equals 5000 milliohms. It's important to note that the maximum incoming line impedance specified by the vendor equipment is 180 milliohms. Therefore, in this case, the cable length should be adjusted to ensure that the impedance does not exceed this value. Let's delve deeper into the practical implications of impedance in electrical systems, particularly focusing on cable selection and ensuring compatibility with sensitive equipment like that found in a hospital setting. Impedance, represented by the symbol Z, is the total opposition a circuit presents to alternating current, or AC. It's a combination of resistance which opposes current flow regardless of whether it's AC or direct current or DC, and reactance, which is the opposition to current flow caused by inductors and capacitors. In AC circuits, impedance is what governs the relationship between voltage and current, analogous to resistance in DC circuits, as described by Ohm's law. However, instead of simply stating that voltage equals current times resistance, or volts equals amps times ohms, in AC circuits we say that voltage equals current times impedance, or volts equals amps times ohms, where impedance is a complex number that accounts for both resistance and reactance. When working with cables, impedance is crucial for several reasons. Firstly, it affects the voltage drop along the cable. A higher impedance cable will cause a greater voltage drop for a given current, which can affect the performance of the equipment connected to the cable. Secondly, impedance influences the amount of current that can flow through the cable safely. Exceeding the cable's current carrying capacity can lead to overheating, insulation breakdown, and potentially fire hazards. Thirdly, impedance matching is important for signal integrity, especially in communication systems. Mismatched impedance can cause signal reflections, which degrades signal quality and reduce the efficiency of data transmission. When selecting cables for a hospital installation, several factors must be considered. Firstly, the cable must be appropriately sized for the anticipated load. This means selecting a cable gauge that can safely handle the maximum current that will flow through it. The National Electrical Code, or NIC, provides guidelines for determining the ampacity of different cable types and sizes based on factors like insulation temperature rating and installation conditions. For example, NEC Table 310.15 provides ampacity tables for conductors rated 600 volts or less, and NEC Table 310.16 provides ampacity tables for conductors rated over 600 volts. Secondly, the cable's insulation must be suitable for the environment in which it will be installed. Hospital environments often have stringent requirements for fire resistance, smoke generation, and the presence of hazardous substances. Cables with low smoke, zero halogen, or LSEH insulation are often preferred in these applications. Thirdly, the cable's grounding and bonding characteristics are critical for ensuring electrical safety and minimizing electromagnetic interference, or EMI. Proper grounding and bonding help to create a low impedance path for fault currents, which can quickly trip circuit breakers and prevent electrical shocks. In the specific scenario described, the vendor equipment has a maximum incoming line impedance requirement of 180 milliohms. This means that the total impedance of the cable run from the source of power to the equipment must not exceed this value. To ensure compliance, you need to carefully calculate the impedance of the cable based on its length, gauge, and material. Firstly, determine the resistance of the cable. The resistance of a conductor depends on its material, length, and cross-sectional area. Copper and aluminum are the most common conductor materials, with copper having lower resistance than aluminum. The resistance of a cable can be calculated using the formula resistance equals resistivity times length divided by area, where resistivity is a property of the conductor material, length is the length of the cable, and area is the cross-sectional area of the conductor. Secondly, estimate the reactance of the cable. The reactance of a cable is due to its inductance and capacitance. Inductance is the property of a conductor that opposes changes in current flow, while capacitance is the ability of a conductor to store electrical energy. The reactance of a cable depends on its geometry, spacing between conductors, and the frequency of the AC power. For typical power cables, the reactance is usually much smaller than the resistance, so it can often be ignored in impedance calculations. Thirdly, calculate the impedance of the cable. The impedance of the cable is the square root of the sum of the squares of the resistance and reactance. In most cases, since the reactance is small, the impedance is approximately equal to the resistance. Once you have calculated the impedance of the cable per unit length, such as ohms per foot, you can multiply it by the total length of the cable run to get a total impedance. To convert ohms per foot to milliohms, multiply the ohms per foot value by 1000. For example, if the cable has a resistance of 0.5 ohms per foot and the cable run is 100 feet long, the total resistance would be 0.5 ohms per foot multiplied by 100 feet, which equals 5 ohms. To convert this to milliohms, multiply by 1000, resulting in 5000 milliohms. Finally, compare the calculated impedance to the vendor's specification of 118 milliohms. If the calculated impedance exceeds this value, you need to take steps to reduce it. This could involve using a shorter cable length, selecting a cable with a larger gauge which lowers the resistance, or using multiple parallel cables to reduce the effective impedance. In some cases, you may also need to consider the impedance of other components in the circuit, such as connectors, switches, and transformers. These components can add to the overall impedance and should be taken into account when ensuring compliance with the vendor's specification. Remember, electrical installations in hospitals are subject to strict regulations and codes to ensure patient safety. Always consult with a qualified electrical engineer or contractor to ensure that your installation meets all applicable requirements. It is also essential to document all calculations and measurements to demonstrate compliance with the vendor's specifications and regulatory standards. In summary, determining the impedance of a cable involves firstly calculating the resistance and reactance of the cable per unit length, secondly multiplying by the cable length to get the total impedance, thirdly converting ohms to milliohms by multiplying by 1000, and fourthly, comparing the calculated impedance to the vendor's specification and making adjustments as needed to ensure compliance. By following these steps and adhering to relevant electrical codes and standards, you can ensure that your cable installation meets the impedance requirements of the equipment and maintains a safe and reliable electrical system. Also, it is important to consider the impact of temperature on cable impedance. The resistance of a conductor increases with temperature, which means that the impedance of a cable will also increase as it heats up. This is particularly important in high current applications where cables can get quite hot. The NEC provides temperature correction factors that can be used to adjust the ampacity of cables based on the ambient temperature and the cable's insulation temperature rating. These correction factors should be applied when determining the appropriate cable size for a given load. Furthermore, consider the effects of harmonics on cable impedance. Harmonics are multiples of the fundamental frequency of the AC power system, such as 60 Hz in the United States. Harmonics can be generated by nonlinear loads, such as electronic devices, variable frequency drives, or VFDs, and switching power supplies. Harmonics can increase the impedance of a cable and cause it to overheat. In severe cases, harmonics can even damage the cable insulation. To mitigate the effects of harmonics, you can use harmonic filters or reactors, which are designed to block or reduce the flow of harmonic currents. You can also use cables with a higher insulation temperature rating, which can better withstand the heat generated by harmonics. When calculating the impedance of a cable, it is also important to consider the skin effect. The skin effect is the tendency of AC current to flow primarily near the surface of a conductor, rather than uniformly throughout its cross-section. This effect increases with frequency and reduces the effective cross-sectional area of the conductor, which increases its resistance and impedance. The skin effect is more pronounced in larger conductors and at higher frequencies. To minimize the skin effect, you can use conductors with a larger surface area, such as hollow conductors or bundled conductors. You can also use cables with a higher conductivity material, such as copper, which reduces the skin effect losses. In addition to the factors mentioned above, you should also consider the effects of aging and corrosion on cable impedance. Over time, cables can degrade due to exposure to moisture, chemicals, and ultraviolet radiation. This degradation can lead to an increase in the cable's resistance and impedance, which can affect its performance and safety. Corrosion can also increase the resistance of cable connections, such as splices and terminations. To prevent aging and corrosion, you can use cables with a durable insulation material and protect them from exposure to harsh environments. You should also regularly inspect cable connections for signs of corrosion and tighten or replace them as needed. When working with cables in a hospital environment, it is crucial to follow all applicable safety precautions. Always de-energize circuits before working on them and use appropriate personal protective equipment, or PPE, such as gloves, eye protection, and insulated tools. Be aware of the potential hazards associated with electrical work, such as electric shock, arc flash, and exposure to hazardous substances. Properly label all cables and circuits to prevent accidental contact and ensure that only qualified personnel perform electrical work. By understanding the factors that affect cable impedance and following proper safety procedures, you can ensure that your electrical system is safe, reliable, and compliant with all applicable codes and standards. Keep in mind that this is a complex topic, and it is always best to consult with a qualified electrical engineer or contractor if you have any questions or concerns. This detailed explanation provides a comprehensive understanding of cable impedance, its importance in electrical systems, and the factors that influence it. By considering these factors and following best practices, you can ensure the safe and reliable operation of electrical equipment, especially in sensitive environments like hospitals.